At this time, we would like to take a moment and review the monitoring section from the Structure Specialist 1 course. The terminal objectives of this lesson are: understand the basic urban search and rescue approach to mitigating hazards in a rescue and recovery operation. Become familiar with the monitoring methods, forms, and tools used in the urban search and rescue environment. Before we jump right in, we should remember the conceptual differences between mitigating the hazards found on a rescue site and monitoring them. Mitigation is typically the practice of identifying a hazard and minimizing the impact of it through avoidance, removal, or repair. Monitoring is the plan of determining movement of a potential hazard through regular intervals of measurement. It is important to remember that monitoring is most effective when tracking slow ductile types of movement. Identifying a hazard. The structure specialist must be able to quickly identify hazards on a site that could affect both victims and rescue personnel. He or she must determine the type of failure mode for the hazard and develop a plan for mitigating or monitoring the hazard. The structure specialist has forms in his toolkit that help identify several potential hazards on a rescue site. These forms are not intended to be all-inclusive, and engineering judgment must be utilized. Form MIT-1 lists several common hazards that may be present on an incident site and are intended to get the structure specialist thinking of the possible mitigation methods. Form MIT-Log is a running log of methods utilized for mitigation. Each of these forms become part of the incident command structure system and will be turned in to the ICS each shift. Mitigation. There are at least 3 distinct levels of mitigation for hazards. Avoiding exposure to the hazard utilizing caution tape, barricades, or other methods of controlling access to the exposure. Minimizing exposure to the hazard utilizing protective clothing or shoring methods. Accepting short-term exposure to the hazard in a risk versus reward environment. Monitoring. There are also at least 3 distinct elements of monitoring. Monitor plan. Details what is to be monitored, methods, and reporting intervals. Record keeping, which validates and communicates the monitor plan. Monitor tools. The items or equipment that will be used to monitor. Trained personnel. Having trained personnel to facilitate the monitor plan. For this presentation, we are going to focus on monitoring. A monitoring plan is going to clearly lay out the details of what is being monitored. It will clearly communicate what items on the site are being used for reference or control points. It will typically have some note to describe the anticipated direction and magnitude of movement. It will also provide the range of displacement that is to be considered dangerous. This information will be used to determine the levels of caution to be taken around the hazard, or the amount of movement that will trigger an alarm to vacate the surrounding area. This documentation becomes part of the overall ICS event record. It must be as clear and concise as possible to be read by personnel not familiar with hazard displacement. The structure specialist must visualize the anticipated failure mode of the hazard in order to determine where, how, what, and when it may fail. Obviously, if the failure mode is not slow and ductile, monitoring the hazard may not yield enough warning time to avoid the hazard failure. The structure specialist must identify monitoring points that are going to provide the earliest indication of failure. The STS must also determine what tool is best suited for detecting and recording hazard displacement. Finally, the STS must determine where the most ideal observation site is to detect the displacement and remain safe throughout the operation. The structure specialist must also identify adequate control or reference points on the site that will enable the measurement of the hazard displacement, provide a coordinate system, and enable re-establishment of that system should the instrument be required to relocate. These control points should be as permanent as possible and be clearly visible from several locations. A reminder that the STS must be able to determine the limits of hazard displacement that would be considered safe. By establishing these limits, Ductile displacement of a hazard can set triggers for caution by rescue personnel or even alarm. Typically, the regular data recording will provide displacement patterns that can be used to establish limits. It is important to note that these limits could be adjusted at any time due to several factors. The task of record keeping is one that must be done carefully and consistently so that the data can be passed on to other shift personnel that may be manning the monitoring station. Keep in mind that these personnel may not be structure specialists. They may not be engineers, surveyors, or construction workers that are familiar with the equipment either. It is also important to note that the monitor logs will become part of the overall incident documentation package. Here is a description of the 4 basic forms associated with monitoring. All 4 monitoring forms would be used to hand off information to the oncoming shifts and will become the Operational Action Plan and/or Tactical Action Plan. MON 1, used to record instrument setup, control and monitoring points. MON 2, for additional setup, control and monitoring points. CP log, used to log the data every time the control points are checked. It would be expected that a new CP log would be created for each operational period or each day. MON log, used to record the data every time a monitoring point is checked. There will be at least as many MON logs as there are monitoring points, and more would be created each day. The monitor forms were designed to be inclusive of several types of monitor plans. MON 1, MON 2, CP log, and MON log were developed for use with the total station and can also be used with a theodolite. MON 1 and MON log should be used with the other monitoring tools such as electronic and laser levels, crack gauges, and plumb bobs. The MON 1 form includes data boxes to record instrument information such as serial number and condition. It also includes boxes to record control and monitor point data, as well as space to create a general sketch of the site to be monitored. The MON 2 form is simply a continuation of the MON 1 form and includes space to record additional information if necessary. The CP log form has columns arranged to facilitate recording repeated measurements of the coordinates of the control points. It is important to note the instrument point or IP that the readings are being taken from. The MON log form is similar to the previous form, except that this is the recorded log of the hazard being monitored. Here is where the structure specialist will begin to develop cyclic patterns of movement in the hazard, which will help to establish caution and/or alarm criteria. While these forms have been developed for use with a total station, they can easily be used to log recorded interval data for other monitoring devices as well. What is important here is to accurately document movement in the hazard and communicate that movement clearly. The various tools that can be utilized for monitoring are theodolite and total station, electronic tilt meter, electronic level, smart level and smart tool, laser pointer or level, plumb bob, crack measuring devices. For the purpose of this learning video, we are going to focus on the theodolite total station. There are at least 3 different methods for monitoring with this instrument that is typically used only for surveying. Method 1. Establish a vertical line that will compare a point on a dangerous building to a point on the ground to detect additional tilt movement. Method 2. Use a control point on an adjacent building and turn an angle to several locations of potential movement on a questionable structure. Method 3. Establish a global X, Y, and Z coordinate system of the site and track relative displacement of discrete monitoring points. The significant advantage of using a survey instrument for monitoring is to observe displacement at a safe distance from the hazard. It is also possible to detect displacement in several locations from one observation location. Some of the most difficult disadvantages are the cost of the instrument and the availability of trained personnel. There are also other disadvantages that may limit the effectiveness of the monitor plan. These are unaccounted displacement of the instrument or coordinate system and the inability to use the instrument with full PPE. The problem with the disadvantages are amplified by the intensity of the rescue environment. Often in the past, these instruments were used by inexperienced personnel utilizing poor methods for error avoidance. This can lead to doubts in not only the total station, but in the role of the structure specialist at an event. Bottom line, this is a great tool, but must be used properly. Often at a rescue event, there are several tasks that may need the structure specialist's attention. This means that the STS must find a reliable person to man the important task of monitoring. Some of the possible non-task force personnel on a site that may be qualified to operate this equipment are Corps of Engineers structure specialists, land surveyors, or construction workers. Not only do these personnel need to understand the instrument, but they must also understand the urban search and rescue environment. To recap the previous lesson, structure mitigation requires initially rapid and then continuing prioritization and planning. Several times, creative solutions with little resources must be identified quickly. Monitoring needs careful planning and the reporting of reliable information. The STS must become familiar with the operation and care of all monitoring tools in the task force cache. Practical uses of monitoring equipment. We would now like to discuss the practical uses of monitoring equipment in the urban search and rescue environment. These topics are total station theodolite use, instrument handling, maintenance and storage, tripod setup and adjustment, setting benchmarks and control points. Total station use. The structure specialist must be able to determine when the use of the total station is appropriate. For example, monitoring a potential catastrophic collapse of a concrete floor may not provide adequate response time for rescue personnel to evacuate safely. The first choice in dealing with the hazard on a rescue site is to mitigate the danger posed. This may be as simple as marking the affected areas off with caution tape and avoiding the hazard. Typically, if there is going to be a period of operation within a potentially affected zone greater than 12 hours, a mitigation or monitoring plan should be established. Bottom line, though, is the total station should be used where feasible. The typical elements required for adequate setup of the total station instrument are transit or theodolite, tripod, plumb bob for establishing equipment location, caution marking tape to cordon off the equipment, control point, documentation supplies, method of anchoring into position, lighting for night operations, marking tools, permanent marker, paint. Several techniques of displacement monitoring are possible on a rescue event site. These could include checking building tilt, checking height of falling hazard, estimating distances using a transit, finding accurate distance with total station, using reflector prism, using reflectorless pulse laser, estimating distance using laser rangefinder binoculars. We have also discussed the importance of proper documentation. Here are just some of the important points. Establish a credible and repeatable routine. Shift change and the transfer of communication to other shifts. Sharing documentation with the incident support team, authority having jurisdiction, or the incident command. And again, that this documentation becomes part of the official incident action plan. It is important to note that there is still quite a bit of engineering judgment required to properly coordinate a monitoring plan in the urban search and rescue environment. Care must be taken to consider all the external factors that may affect the displacement of the monitored point. The proper handling of this sensitive equipment is crucial to the accurate and dependable performance of the total station. Always carry the instrument in its case. Never place the instrument on the ground. Do not hold the two standards to carry the instrument around a job site. When leaving the instrument set up, place the lens cap on and cover the entire instrument with the vinyl cover. This will help protect the instrument from the elements such as rain, wind, which could bring dust and debris. It is also important to transport the instrument in its case with all appropriate measures taken to properly store all loose items. When the instrument does become wet, wipe the instrument carefully. Remove the foam inserts from the case and let them dry out completely. When everything is completely dry, only then should you place the instrument back in its container. Moisture can also affect the instrument during storage. During surveying operations, it is important to wipe rain off the instrument with a clean cotton cloth. The instrument should be totally clean before returning it to its case. This means brushing off the lenses with a soft cotton cloth, breathing on them, careful to never touch the lenses directly with your fingers. Never use liquids such as oil, benzene, water, or detergents to clean the instrument. Other maintenance tips to follow are regularly checking the tripod for any loose or defective parts. If parts are found to be damaged or missing, immediately contact the manufacturer or instrument salesperson. Other items to be aware of are condensation or mold on any of the internal surfaces of the telescope, foreign matter clogging threaded or movable components. Also be aware of dents or scratches indicating that the instrument has been dropped, which may affect the smooth operation of machined parts, causing further damage to the instrument. Good practice when bringing the instrument back from a deployment or training exercise is to let it dry out a few days outside of its case. This helps to prevent mildew and fungus. But the storage area should be dust-proof, have good air circulation and low humidity to prevent further damage to the instrument. In extreme cold, don't take the instruments indoors during non-working periods, but leave them in a protected place at outside temperature. This will help to prevent condensation. As a reminder, here is the basic setup procedure for the total station. Additional setup instructions are found on this training video. To set up the tripod, loosen quick clamps or twist locks on legs. With tripod closed, raise the tripod head to about chin level. Tighten leg locks. Spread the tripod legs so that the three shoes form an equilateral triangle and are fixed firmly in the ground. Adjust so that the tripod head is approximately level and positioned directly over the surveying point. 1. Mount the instrument on the tripod head. Tighten the tripod centering screw. 2. If the instrument has an optical plummet, turn its eyepiece to focus on the reticle. Then push or pull the eyepiece to focus on the surveying point. 3. Turn the foot screws to center the surveying point in the reticle. 4. Look at the circular vial. Observe the off-center direction of the bubble. Shorten a leg nearest to the direction, or extend a leg farthest from the direction. Generally, 2 legs have to be adjusted to center the bubble. 5. Final leveling can be completed by adjusting legs and/or turning the leveling screws to complete centering of the vial. 6. Look through the optical plummet again. If the surveying point is off-center, loosen tripod centering screw and slide the instrument on the tripod plate to center the surveying point on the reticle. Tighten the center screw. Recheck leveling of the vial. Again, this information will be covered in detail later in this training video. But one item that bears reiterating is establishing bomb-proof control points that can be later used to either establish or validate a coordinate system. It is desired to define at least 2 bomb-proof control point locations by sending someone to each. Set target, measuring the target with the total station, and record the coordinate. These points will be called CP10, CP20, CP30, CP40, and so on. Identify point or points on structure or structures that you need to monitor, and set or find precise target. These points will be called MP100, MP200, MP300, and so on. Above all else, though, understand that if a structure is badly damaged, it may not be safe to set a target on that structure, and all that can be measured is the structure itself. Final key learning points from this review are that a calibrated total station instrument may be more effective in monitoring than a theodolite. Electronic measuring devices may be very useful in the urban search and rescue environment, while the quality and durability continue to improve.